Alright everybody, welcome back. Today we're going to be looking at surface area, and the surface area that we're going to be looking at is going to be the surface area that's made by this multivariable function. And a multivariable function where we're going to have some x and y coordinate pairs exist in some region D. Ideally, we want this region D to be in the domain where z is going to be defined. Now, this must happen if f of x and if f sub x and f sub y are going to be continuous. In other words, the first order partial derivatives for this given multivariable function must be continuous. If that's the case, then this double integral over that domain or over that region for the square root of the squares of the sum of the squares of the partial derivatives must be the surface area. Now, if you remember back from Calc 2, in Calc 2 we did a very similar object when we were talking about arc length. We also did this back in Chapter 13 when we were talking about the arc length of any given curve. It should look very, very similar to this equation. Alright, if we don't want just the arc length, because the arc length is just this one-dimensional length, we want now a surface area, which means we're going to be integrating with respect to two different variables. Typically we go with x's and y's. Now, for the example that I have on here on the screen, it says find the surface area of the part of the plane, which is given by 3x plus 2y plus z is equal to 6, that lies in the first octant. Alright, so we want to get a visualization going. What does this mean for us? Alright, so given that quick visualization, what I'm going to do is I'm really quickly going to go over, you know what, I'm not going to go to Geogebra just yet. I want to go ahead and attempt to just give a quick sketch and then see if Geogebra matches with our sketch. Alright, so the first thing that I'm going to do is I'm going to get my x and y coordinate system in here, and I'm going to start there. Alright. Alright, so here's my axes, x, y, and z. Now I'm going to go through and I'm going to start figuring out what are the x, y, and z intercepts. So whenever I'm trying to find my x-intercept, I set both y and z to 0. So if y and z are both 0, then that naturally means that x is going to be 2. Now to find my y-intercept, if x and y are both 0, then that means y must be 3. Alright, now to find my z-intercept, if both x and y are 0, then that means that z is going to be 6. And so here is my surface that I'm looking at. It's going to look like this. Let's bring it back down this way. Perfect. So here's my surface that I'm looking at right in here. So again, it's only the surface made by this plane. Alright, now I want to go through and I want to go to Geogebra, see if Geogebra agrees with what I have here. So follow me along to the class on Geogebra. Alright, so here's Geogebra. Alright, I have the 3D graphing system going. Now I have the equation of the plane here. So this equation was the equation of the plane that 3x plus 2y plus z is equal to 6. And I put the coordinates here, a, b, and c, as the coordinates for the intercepts for the x, y, and z coordinate respectively. So here we see x coordinate at 2, 0, 0. Then we see the y point at 0, 3, 0. And then we see the z point at 0, 0, 6. And on our picture, this is all that we have here, and this is how we're viewing it. So if we wanted to view the plane here, then we can go ahead and draw the plane in, and then we could go ahead and see it. But for the purposes of this problem, this is all that we want. We want to figure out what is that surface area there that is made by the first quadrant and this plane. So let's go ahead and now that we know that our visual was correct, let's go ahead and let's find this out. So let's go back to class. All right, here we are. Now, if I want to go ahead and find this specific surface area, I need to go through and I need to figure out, well, what is this function here? Well, according to that function, I have that 3x plus 2y plus z is equal to 6, which would then tell me that z is equal to negative 3x minus 2y plus 6. And this here is my function with both x and y inputs. So as I'm looking at this, I just want to take my partial with respect to x, which should be negative 3, and my partial with respect to y, which should be negative 2. Now, to find this surface area, it's just going to be the double integral over that specific domain. Now, the domain, I'll come back to it in just a little bit, but here I want the partial, negative 3 squared, plus the partial with respect to y, that's negative 2 squared, plus 1. There we are. Now I need to figure out how I'm going to write this up for my actual domain that I'm working with. Since this is made in the first octant, I want to look at the first, again, quadrant. So let's go through and let's look at this domain or this region on the x and y coordinate system. Once we see it on the x and y coordinate system, we'll be able to identify what type of domain or what type of region we're trying to integrate. So here's my x and here's my y coordinates. I'm going to get a semi of a good grid going here. 1, 2, 3, 4. Oops. There we are. Alright, so I know by the picture up here that my y-axis or my y-intercept is at 3, my x-intercept is at 2, which means I'm looking at this line here, just like this, and that's the original equation that I'm observing here. That original equation is that 3x plus 2y is equal to 6. In other words, when z is equal to 0. So looking at this region, I want to set up a double integral using that region. So the big question is, do we want to get vertical heights first, or do we want to get horizontal heights first? Again, that's a big question. And for this type of problem, it is completely up to you. Alright, so if it were up to me, I would probably do vertical heights since I'm somewhat comfortable with vertical heights. So I'm going to go with vertical heights here. I only need one double integral because my vertical heights never change. The bottom is always the x-axis and the top is always this blue line for that region. So what's the bottom y value? Well, the bottom y value, that's just 0. Alright, what's the top y value for this height? Well, this height has a y value of this line. That y value is negative 3/2 x plus 3. So that top part of that height is negative 3/2 x plus 3. Now, these heights, they change as we start moving through this interval, and that's the x interval that we're now integrating over. That interval is from 0 to 2. Now remember, these heights, the innermost integral first was dy, excuse me there, the first one was dy because we wanted our heights to change. The second integral, the outermost integral, changed our x values. So this is the integral that we want to set up. Alright, and we can go ahead and we can solve this integral. All we're doing is just integrating a constant, which will be pretty nice. So my answer here, again, you could put pause on this video, put pause and go through, And you should get... Did you put pause? Did you really? I'm waiting. You can put pause. No, really. Put pause. Try it out. Here we go. 3 root 14. That should be your answer. Now, what if you did not set up with vertical heights first? So let's go ahead and let's look at that integral. Let's see if we could set it up the other way. This is still going to be 9 plus 4 plus 1, so that's still going to be 13. And I want to do dx dy first. So if we're going to go do dx dy first, we need these horizontal heights first. And you know what? I'm going to do this in orange. Whoa, where'd okay, so I'm going to do this in orange here. That way we can see it a little bit more clear. So I want these horizontal heights. Notice the horizontal heights from left to right. Left, that's going to be the x value of 0. The rightmost, it's going to be this line. So in order for me to grab this line, I need to go ahead and I need to solve this equation for x. So solving this equation for x, I'm going to get that x is equal to negative 2/3 y plus 2. And that's going to be my top part for this horizontal height. From the left, that's x is equal to 0. From the right, it has a height of negative 2/3 y plus 2. Alright, well those heights, those horizontal heights are changing for the y values. Those y values, and that's my dy here, are changing between 0 and 3. And I guarantee you, if you go through and if you solve this on your own, alright, again, making sure you know how to do this, your answer should be 3 root 14 as well. So again, completely up to you. Do you want to do this using vertical heights or horizontal heights? Whichever way you do it, you should get the right answer. Alright, awesome. So now that we have more of a feel for this, let's go ahead and let's do another example. In this example, we're going to want to determine the surface area of the part of z is equal to xy that lies in the cylinder given by x squared plus y squared is equal to 1. Alright, so determine the surface area of the part of z is equal to xy. Alright, so z is equal to xy, that's a hyperbolic paraboloid that lies in the cylinder given by x squared plus y squared is equal to 1. Alright, so we're going to need my old friend Geogebra here. So let's go pay Geogebra a quick visit before we get started here. Alright, here's Geogebra, here's my old friend. And what I want to do is, if you guys can follow along, I'm on the multivariable class for Geogebra, the link that I sent you all. And I want to go to this one right here, the one that says surface area. So I'm going to click on that surface area here, and it's just a little applet here that I developed. Alright, so we see the x, y, and z coordinate system here. Alright, it's looking good. Let me go ahead and zoom that in. There we are. Alright, now, excuse me, my computer's lagging a little bit. I'll wait for that. So I'm going to show the surfaces here. So I'm going to go through and here are the surfaces. I have the green surface, which is my hyperbolic paraboloid, and I have the red surface, which is my cylinder. Now notice it's kind of hard it's kind of hard to tell which one is the intersection or where it's actually occurring. So I actually took the liberty to parameterize that intersection, and I have it here. So the intersection, again, is the hyperbolic paraboloid here is intersecting with the cylinder, and it's making this type of surface. And what I want to do now is I want to find that surface area. All right, so that's going to be our job, is to find that surface area of this Pringle shape, right? So I don't know if you guys remember me telling you this was one of my favorite shapes, and it pops up a lot in multivariable. All right, so we're going to go find out what type of surface area these Pringle chips have. All right, so let's go back to the class. All right, here we are. So what I want to do then is I want to start talking about the domain, right? If we can view the domain, then we can go ahead and we can try to extract what it is that we're looking at. All right, so as I'm looking at this, I'm going to start trying to think about, well, let's project all of this onto the X and Y axis. If we project all of this onto the X and Y axis, then we naturally will get some random domain, or we're going to get some domain that we're going to be looking at. So let's start there. Let's put this onto the X and Y domain. All right, here we are. I'm going to go with the circle here. And it's a circle because, again, we were looking at the top view for that X and Y axis, X, Y, and Z axis. Looking from the top view, that means we only get to see this circular portion, but the circular portion is filled in, making this surface, and that part of the surface was at Z is equal to XY. So given that Z is equal to XY, well, if Z was equal to, let's say, f of xy, which is given by xy, then if I take the partial derivative, with respect to x, then naturally I get y. And if I take the partial derivative with respect to y, then naturally I get x. So notice the domain that we're integrating over. It's a circular domain. Double integrals, so double integrals over a circular region, I kind of want to use polar coordinates. So I'm going to say here use polar coordinates. Well, if we use polar coordinates, then we're going to have to go ahead and we're going to have to modify this just a little bit more. All right, now here goes the modification that we're going to be using. All right, so this is going to be the area of the surface that we were initially looking at, and this is going to be the double integral for the square root of, and again here we're going to have the partial of x, which was x squared, plus the partial of z sub y, that's going to be y squared, or sorry, z sub x, that's y squared, z sub y, that's x squared, and then this is going to be plus 1. Nice. Now we're going to go ahead and we're going to use polar coordinates here. So since we're using polar coordinates, the first thing that we have to do then is we then have to figure out what is the radii extending through. So this radii is going to extend from 0 to 1. So radii extends from 0 to 1. All right, there we are. And it's extending from 0 to 1 at all times. Anywhere on this given region, it extends from 0 to 1. Nice. Now, theta. Let's go ahead and let's start traversing for theta. Theta is going to make sure that as your radii is increasing, or your radii is moving, your theta value is going to move as well to make sure it starts capturing that area. Theta here moves from 0 all the way across to 2 pi. Now, because we changed into polar coordinates, this is now going to be r dr d theta. R dr d theta. It's perfect. Which means this double integral is really from 0 to 2 pi, from 0 to 1, x squared plus y squared. You remember what x squared plus y squared is in polar? It's r squared. Then we have r out there, and this is r dr, d theta. Nice. So from here, we can just take it with a u substitution, and everything will be fine. So I'm going to say just do a u sub here, and your u sub, you're going to do u is equal to r squared plus 1, and you should be able to get it from there. So take some time, get that integral done, and make sure you arrive at this conclusion that your answer in explicit form should be 2 pi thirds multiplied by 2 to the power of 3 halves minus 1. This should be your final answer. And again, that final answer was just looking at this surface area. Right? It was just looking at this surface area that we were looking at here. The surface area of this Pringle chip. Right? You can see if we view it from the top, it looks more of that circular domain that we wanted to observe. Nice. All right, let's go back to class. Now that we see this. Perfect. So let's go ahead and let's try a different example now. All right, so here goes this example. We want to find the surface area of the portion. Whoa. What was that? I don't know. Here we are. Alright, so hopefully we don't have any more of those movements here. So find the surface area of the portion of the sphere. Let's say z is equal to square root of 4 minus x squared. That lies above the rectangle R in the x and y plane, whose coordinates satisfy that x is bounded between 0 and 1, and that y is bounded between 0 and 4. Nice. So, let's go through. Now, the nice part about this is, again, we have this surface area that we want to investigate. So this surface area is going to be the portion of the sphere, all right, portion of the sphere, and actually it's not portion of the sphere, yeah, because that's not a sphere, that's a cylinder. I have no idea why I said sphere. My apologies, my sincere apologies. Portion of the surface. And again, because this is a cylinder, not a sphere, so portion of the surface that lies above the rectangle whose x and y coordinates are here. Awesome. So really quickly, what I'm going to go do is I'm going to make my grid really quickly. All right. Alright, so here we go. So actually, let me make this slightly bigger. It's going to go from 0 to 1. There we go. Perfect. Alright, so the region that we're looking at is the x values are going to go from 0 to 1, and the y values are going to go from 0 to 4. So from 0 to 1, there we are. This goes from 0 to 1. Nice. And then the y values go from 0 to 4. There we are. And we have this rectangle region, or that rectangular region. Now, the nice part about this is that we are going to be able to use Fubini's theorem here because we're going to be integrating over this rectangular region. So that's always going to be nice. All right, Fubini's theorem will be applied here if we would like. Now, I'm going to make this slightly smaller. There we are. And let's put that as our x-axis. Perfect. So right now what I want to do is I want to try to visualize this. Visualizing this is going to tell me that I have some sort of cylinder elongated across the y-axis, because again, we're not given a y-coordinate. This means that there's going to be all circles, concentric circles, centered about the y-axis with a radius of 2. All right, now what I'm seeing here, and I'm going to try to do this in green here. So if z is equal to 4 minus x squared, like such, then I'm going to take this as my function, f of xy. But before I do that, I'm going to make this z squared is equal to 4 minus x squared, which means in this particular case that x squared plus z squared is equal to 4. Nice. Alright. It's not looking too bad so far. Alright, it's looking pretty good. So now that I have this, I want to go through then and I want to start looking at this cylinder. Alright, so in order to look at that cylinder, I need my coordinate system. So that's exactly what I'm going to do. I'm going to draw my coordinate system here. Alright, so here's my x, y, and z. And again, I'm going to have these circles moving around the y-axis because again, only have x's and z's being with a radius of 2. So as I start looking at these circles that look like this, we can start connecting them to make this cylinder figure that is going to extend along the y-axis. Alright, now if it's extending along the y-axis, again, that's going to be nice. It's all going to be nice here. And the reason I say that it's going to be nice is because we have this small rectangular region. So that small rectangular region is going to go out to x is equal to 1, and then y is equal to 4. So when we look at this, let's say this is x here. It's kind of like we're cutting out this small little piece here. And this is the surface area that we want to observe. Now that we get a quick visualization, let's go look at it on Geogebra. So here we are, Geogebra for the class, and instead of the surface area example, I want you to go to surface area stuff. Alright, this is part 2, so it's part 2 of stuff for the surface area. Alright, so here's my surface, and again, I only parameterize the surface here to show that we only had this one top surface of that cylinder. Alright, now when we view this top surface of this cylinder, I'm going to make sure that I'm looking at my x and y coordinate system, alright, to make sure that I have this rectangular piece right in here. X is equal to 1, y is equal to 4. Now, when this happens, and again, let me move it in here. When this happens, what we're looking at here, oops, let me try to move this here. Wow, that's not working out for me. So give me one quick second and I will reorient this. There we are. So as I'm looking at this, I only want that one strip here. It looks like a rectangle from above, from the X and Y coordinate system, but again, because it lies on this cylinder, it has more of an arc to it. So we want to find that specific surface area here for this rectangular piece that's going to sit on that cylinder. All right, so let's go through and let's find that surface area right there. Let's go back to class. Here we are. All right. So it's looking pretty good. We got some stuff ahead of us. Now, one of the things that you're going to notice, the cylinder, that coordinate system is given by a function that's given in terms of x's and y's, but there's a slight issue with it that we don't have a y value. And that's perfectly fine. Again, I said it might be an issue. Some people might see it as a godsend, because when we take the derivative of that function, of this function here, taking that derivative with respect to y, we actually just get 0, because again, we have no values for y. Now, the partial derivative with respect to x, well, that one's a little bit more difficult, right? The function here is just going to be 4 minus x squared raised to the power of 1/2. So drop the exponent forward, subtract 1 from the exponent, and then multiply by the chain rule on the inside. Naturally, we're going to get negative x over square root of 4 minus x squared. And again, we can just double check this. Really quickly, go ahead and do a double check. Make sure that this is the derivative that you obtain. All right. Now, in the whole process of having this done, what I want now is I want to find the area of that surface. So I'm going to do a double integral. Again, Fubini's theorem is applicable, which means it doesn't matter whether I do dx or dy first. But I want to take the squares of my partials. So the first one's going to be 0 squared plus the next one is negative x over the square root of 4 minus x squared squared. And I still need a plus 1. Plus 1. Here we go. And now, again, your differentials, you could do dx or dy first. Again, at the end of the day, it doesn't matter, because Fubini's theorem says we're on a rectangular region. We're allowed to choose whatever we'd like. For the purposes of me doing this, I'm going to go with x and then y. So my x values are changing between 0 and 1. So x is between 0 and 1. The y values change between 0 and 4. So we're good so far. All right. Looking good? Awesome. So now that we have this, let's go ahead and let's start making this integration piece here, or this integrand. Alright, this is going to be the integral from 0 to 4, then the integral from 0 to 1, 0 squared, that's nice. So then this piece is going to be x squared divided by 4 minus x squared plus 1 inside of that square root, and that's dx dy. Again, I want to make sure that I go through the whole process and make sure that I simplify this as much as possible. Alright, now that I have this, I'm going to go through, and my numerator here, whoa, ¿qué pasó? Cheese and crackers. There we are. Okay, so let's go through my first part here. So the first part, so that's going to be x squared plus 4 minus x squared divided by 4 minus x squared, and that's all inside of the square root. And this is all dx dy. And again, it's still inside of the square root, because all I'm doing is combining like terms on my radicand. Integral from 0 to 4, integral from 0 to 1. The x squareds on that numerator cancel, and we're just left with 4 divided by 4 minus x squared And this is all in the square root, which makes it real nice because, again, now we just look at this given function. All right, there we are. And that's dx dy. Perfect. So if we have to integrate with respect to x first, that's great, because here we're going to, here I believe we have arctan, if I'm not mistaken. We have this one integral where we have a squared minus u squared. Alright, and then this is equal to sine inverse of u over a plus c. Which means the innermost integral should be 2 times sine inverse of 1/2 x, and that's going to be evaluated from 0 to 1, and then that's going to come with dy. That looks really good. So from here, I want you to go ahead and take the integral from there. Finish that evaluation for this integral. All right, once you do, you will get an answer of 4 pi thirds. All right, so when we're looking at the surface area here, the surface area is 4 pi thirds. And that's all there is, folks. That's all there is for surface area at this time. So I hope you all enjoyed this, and I hope to see you all soon. All right, stay safe.